So then the next thing I wanted to do was to add to a comment or to an answer that was posed last time. It was regarding the two integrators loop uh, filter design, and the question was, why did the high pass transfer function had an amplitude of 1, and then we had some constants in the band pass and the low pass. The reason, and I said, well, this is from the prototypes, but to really amplify that, I wanted to say that the reason that is because we define the primary input, if you remember, as the high pass filter response. And the reason that's appropriate is because the high pass is the one, remember that this is a second order system. The high pass is the one that has all the zeros. It has both zeros defined in the transfer function. So when we define it as the first or the primary output or the main output, we end up with a constant of 1 for the amplitude in the transfer function. Then to get the band pass, we integrate once, so we get rid of 1 0, and then to get the low pass, we integrate twice to get rid of all the zeros and get a all pole low pass filter. And as we integrate, then we pick up constants, and those responses then have those constants show up in the transfer function. So hopefully that clarified that further. Okay. I also wanted to do a problem as a matter of example in chapter 14 on filters, and this is problem 13 from the book. I'm going to read it. Well, first I'm going to switch to the pad, and then I'm going to read it and work it out. So this is a typical problem, something that you would get on a test, for example. Okay. So let me do that. So this is problem 13 in chapter 14 of the book. So problem 13 says the second order low pass filter has poles at minus 0.25 plus or minus j, and a transmission 0 at omega equals 2.5 radians per second. And then it asks the following question: if the DC gain is unity, give the transfer function T of S. And also, what is the gain at omega approaching infinity? Okay. So let's do that. All right. So problem 13. So the first thing is take the information that we were given, and which were the zeros and the poles, and just write out with that information the transfer function. So then the transfer function would be, now we have to remember that for this, the general form for a low pass for this type of filter, again from the prototype, is going to be some type of K. This is where the 0 was. So remember, this is the form so that would be that 0 that we were giving square. And then the two poles. So that's the first one, and this is the second pole. And then we can just multiply that out, and we get same thing in the numerator. But in the denominator we get so that would be our transfer function. We have to find K, and we were given that the gain at DC was unity. So what that means is that, so we have that information, okay? And then if we just zero out S, we get that 6.225K over 1.065, and that's going to give us a K value of 0.17. Okay, so now we have K. Therefore, we have everything we need to know about the transfer function. So now the transfer function becomes and then the second question was what is the amplitude as the frequency approaches infinity. So we want to know what is okay, and then I'm not going to do it here, but if you remember your calculus, the L'Hopital's rule, and as you take the limit as s goes to infinity of T of s, so you apply the L'Hopital's rule and differentiate, and what you're going to see is that as s approaches infinity, this is going to approach 1. Okay, so what that means is that the transfer function at infinity in the frequency domain is going to be 0.17. Okay, and that's problem 13, an example that it fits well with what you would get in a test. Or I think this would be on the easy side of what you would get in a test, but it still it would be appropriate. So any questions about problem 13, what I just went through?
Yeah, Dr. Nens, I actually had a question about that too.
Right.
So if a question says like it has a high frequency gain of unity, does that also mean that T of 0 equals to 1?
If it says that it has a high frequency
gain of unity.
So I don't think you will get a question like that, because it's not being quantified. You could say if it has a gain of unity at infinity, that's different. But a high is not, is ill defined. Notice that they told us that this had a gain of unity at DC, and we know what that frequency is. That is a 0. So that's a number.
But if I was just saying, for like hypothetical, like second order high pass filter, if it's a high frequency gain of unity, does that also mean T of 0 equals to 1?
No.
Oh, okay.
No, but what I'm saying additionally is that it should not be phrased that way. it should be phrased, for example, the gain at for the high pass, the gain at infinity, it is unity. So that actually quantifies it mathematically, because as you can see, we can actually derive an expression for that for t of infinity, but we can have an expression for t of high frequency. We don't know what that is, right? Unless they give you a specific frequency. Do you see what I'm saying?
Yeah, that makes sense.
All right.